Okay, then we start our exercise, and first we're going to draw our schematic. So this will be RS, so resistance. Then we will have our amplifier here. So this will be plus, minus, minus, plus. And then this is going to be V out, R1 and R2. Then we will replace this circuit with our noise model, and in our noise model what we have is we have let's delete this one. What we have it is first we have the noise of this resistance VRS, we have resistance RS here, then we have resistance noise input reference noise voltage of this resistor R1 in parallel to R2 as we found previously, and then we have the input reference noise of the amplifier itself, and then input reference current of the amplifier, and we can actually forget the two-port network. So we are going to start moving this noise source towards the left. So what we're going to do now is that this is already in series, so there is no change. This needs to be moved also towards the left, and let's do that very quickly. So we continue here. The model for this one will look like this. So we have VRS, we have V12, then we have Vn, and then we have RS, and then we have R1 in parallel to R2, and we have the current source here, so this is IN. Okay, so we continue. We are going to convert this current here. We need to convert it into voltage, so we convert this Norton to Thevenin equivalent with these two resistors. So our model will be like this at the end. You can have it like this: VRS, V12, Vn, and then this voltage source is equal to IN multiplied by RS plus R1 in parallel to R2, and then we have resistors R1 parallel to R2. Okay. And then that's it. I have all the noise sources as series voltage sources to the left, then I can calculate the total noise. So the total, I will call it total input reference noise, is going to be equal to, and it will be VRS plus V12 plus Vn plus In multiplied by Rs plus R1 in parallel to R2. And we continue Vn tot. We remember that if we assume that we are going to have a single input common source transistor, then we have that En, it is going to be equal to Vn G omega C, the total capacitance at the input, if we are under the assumption that we are going to use a single input transistor like this common source amplifier. For completeness, if we are going to use a differential pair at the output, we have to take in consideration that my Vn of the whole differential pair, it is going to be equal to square root times Vn, and that In of the differential pair, it is going to be equal to In divided by square root of 2, because of the reasons that we discussed before, how the ABCD matrix of the differential pair looks like. So when we refer the input noise sources, basically the power of the noise voltage squares, and add then the noise current squares, then it is divided by 2. But now we are going to assume that just for simplicity that we're going to have a single device as input. Then we can continue writing the equation here. So this will be Vn plus Vn G omega C, and this multiplied by Rs plus R1 in parallel to R2. And basically at this point we can just factorate this a little bit nicely before we find the power. Okay, now we can square this one. We find the power spectral density is equal to VRS square plus V12 square plus Vn square, and then the real part, it is 1 squared plus, and then we have omega square C square, and then multiply by this part squared. Okay, and then we can replace the equations that we have for the different parts. Square, this is going to be equal resistance, the noise over resistor, 4 kT Rs. Then we have V12. V12 is 4 kT R1 in parallel to R2. And then we have the noise of the input transistor, and then we can use either Vn square equal to 4 kT gamma divided by Gm, or Vn square 2 kT divided by Ks, that is the inversion coefficient, multiplied by Gm. So they are almost the same. Since we want to work as much as possible close to the weak inversion, we are going to use today 2kt over ks gm, but the error that we make, it is very little. The difference between both of them it is very little, so it really doesn't matter. So let's take this one, 2kt ks gm, and this is going to be multiplied by 1 plus fc divided by f, and then this one 1 plus omega square c square rs plus r1 in parallel to r2, this square, and again omega is equal to pf. Very good. Then we have a very nice equation here that relates the feedback resistors and the small signal parameters of the input transistor with the input refer noise spectral density. And we can use this equation to do noise optimization. Now we are here, our resistance, we know from the instruction that we got for this exercise, this resistance, it is 1 kilo ohm. So we can calculate this value here. We have this value, and then we also know that the gain of this amplifier, it is going to be, the gain of this amplifier is going to be a factor of 10, and we also know that the bandwidth of interest, it is between 1 kilohertz and 1 megahertz. So we are going to concentrate on this area. So the first conclusion that we can have here is that these factors here and the factor here, they must be smaller than 4kT RS in order not to degrade substantially the noise performance. There is a number of details that it is important to discuss here, depending on the type of amplifier that we are designing, on the specification that we have for noise. Then we have to make some design choices. In low noise amplifiers, we will want to minimize as much as possible the contribution from the feedback resistors and also the contribution from the input transistors in the amplifier. But we can already see here some implications of reducing the noise. Let's take it first, the resistors. We take the resistors here, R1 and R2. If we make these two resistors very small, the current that I will need to handle signal swing at the output will increase. The output will typically be connected to a load also here. Will be connected to a load, and it is also connected to the feedback. And then I will need some current to be able to produce a signal swing at the output. And then if I use very small resistors, then I will need a large current at the output just to be able to drive those resistors. So I have a limitation already there, that reducing the input referred noise that it is coming from the resistors, it will cost some current. This is from this part. So it is possible to reduce, but I will have to put a lot of current at the output in order to drive those resistors. The other consideration, it is a GM, as we saw. GM in a weak inversion. GM is equal to IDC divided by KS times the thermal voltage that we have defined as phi t was phi t. So sorry, this is wrong. It is Ks divided by the thermal voltage. Okay, so then the problem here is that I will need to put quite a lot of current here in order to decrease this factor here. So this directly showing it here. It will be required to put current in order to increase the transconductance, and then I also should remember that GM in a strong inversion, on the other hand, it is proportional to the square root of IDS. So then it is very costly to increase the transconductance to try to keep this value low in strong inversion. So I have to be careful how do I generate this transconductance. Okay, so we have a specification, we know this value, and the resistor it is 1 kilo ohm. So when I take this value and I'm plugging it here, the noise resistance of 1 kilo ohm resistor, it is going to be around 4 nanovolt per square root of hertz. I mean, if I square it, I will get 4 kTRS. I take the square root, I will get 4 nanovolts. That means that this value has to be much lower than 4 nanovolts, and this value also has to be much lower than 4 nanovolts per square root of hertz, so that it will not add much noise to my system. Okay, so depending on the application, we will require a lot of noise performance, very good noise performance. Since we don't have here a specification, we will just make some assumptions, and for today the assumption will be that we are going to let the feedback and the input refer of the noise of the amplifier to include around 50% of the noise, add 50% of the noise. That means that around 50% of the noise will be coming from the input, the source resistor, and the rest is going to come from the feedback and the amplifier. Sometimes I can tolerate more noise. As mentioned before, it depends on the signal to noise ratio that my system can tolerate. The signal to noise ratio will be mapped to an analog to digital converter, the quantization also the digital analog to digital converter, and then that will set the noise floor that I can have. But since we don't have those characteristics of that information right now, we are just going to assume that we are not going to deteriorate too much the noise, and that we are just going to raise the noise floor 3 decibels. That means that 50% of the noise will come from the source, and 50% of the noise will come from the other components. Okay, so now how do we use this equation? Let's see. We have naturally to test this equation, and then the easiest way to do that is to use either a MATLAB script, Octave can also be used, Python script, or any other language that you will want to use, and basically plug in the variables and simulate this curve. So I prepared a script here for you to take a look, and I'm going to be also uploading this one as part of the material of the course. So this equation, it is basically here the equation that we extracted right now with hand calculation here, and I'm going to be sweeping this with values from different frequencies. I can set up the frequencies here. And just to test it, I'm going to do it from 1 kilohertz to 10 gigahertz. And then you can give values here. Where do we extract these values? We need values for transistors, and then we have really good tools for that we studied. We saw these tools in the lecture number 2. So we're going to go very quick. We have a tool for doing characterization of a device. Now, we just put the voltage drain to source of the device that we want, the current that we want to test, the dimensions of the length, width, number of fingers. So we're going to use these values to do some simulations, and then we can in principle start with any number and then just start checking what happens. So we're going to start with this one, for no particular reason. 50 micrometer width transistor, 180 nanometer length, and a current of 500 microamp. So the first thing that I'm going to do is that I'm going to extract the GM/ID curves, and then the FT and transconductance, and then for that I have already prepared this script that we discussed in the lecture on devices. Then this script is going to read the values of this, or the sizes and of the transistor, and produce all the curves. So we're going to send this one to simulation. Okay, now it is done. So we have the following plot. So we have GM/ID, we have FT, and we have transconductance. So the first thing that I'm going to do is to put this in log scale, and then I'm going to separate the plots and put also the current in the log scale. So we have GM/ID, FT, and transconductance as a function of the drain to source current. So it basically was a drain to source current sweep and extracting all these values. And here I'm going to use a vertical marker and let's start to check for this particular size of transistor. And let's take it a look again which size it is. We have a 180 nanometer transistor, 50 micrometer width. When we sweep the current, we have that the transistor is in very weak inversion, and then we have almost 1 microamp here, and then the GM/ID start going slowly down. We have 10 microamps in this point, and then we have different values here. So so from this plot we can take a look and check the transconductance that I will need. Okay, transconductance values that I will need to fulfill my my requirement. And then I see for this particular size of transistor the transconductance values above, let's say 2 millisiemens. We can see that the transistor is entering very strong inversion, and then the transconductance doesn't really grow very much here. Okay, so this is for this size of transistor. But how much transconductance do I need? That is a good question. We go back to our our equation here, and then we see that we want to split 50% of the noise budget between the feedback resistors and the MOS transistor. Then we have to give values to R1 and R2 for this purpose. Since I have a gain of 10, and remember that the gain in this amplifier is equal to R1 plus R2 divided by R1, then I can start giving values to these resistors so that they accomplish this requirement. So the parallel combination of R1 and R2 have to be in principle lower than around I mean, if we want to give 50% here, 25% here, and 25% here, then these resistors, combination of these resistors, have to be at least half the source resistors. This source resistors was 1 kilo ohm. The source resistor was 1 kilo ohm. So this parallel combination I can set to values, for instance, let's see, I can put, for instance, R1 in 300 ohms and R2 in 2500 ohms. Okay, so the parallel combination of these two will give me, let's see, very quick, it's 300, 500, it's going to give me 270. So the parallel combination will give me 270 ohms. So it is it is a value that will accomplish this requirement. No? So I will set these ones in 300 and 2700. I can put other values if I want. For now, we are going to set these ones to these values. We will see later how good or bad they are. And then this one, on the other hand, for that one, we can start with, let's say, we can start with 1 milliamp here. Let's see, it's 1 milliamp. With 1 milliamp, for 1 milliamp and for this size of transistor, what we have is that the GM error ID is 11. It is not very high. The frequency performance is actually very good, 23 gigahertz, but the bandwidth of our system, it is just 1 megahertz, so we are very large bandwidth. So maybe we can exchange some of this high performance bandwidth, and we have 11 millisiemens. So we can probably plug in these values and see what happens. So for this transistor, what I'm going to do now, I am going to extract with the self and MOS template that we have here. I'm going to extract the values of transconductance. Let's put it in 1 milli here. One milli, and then we run the okay. So we extracted, and then For 1 milliamp, we get the following solution. So we're going to put this one in our MATLAB template. Let's see, our MATLAB template is here. So let's comment these ones. So we bring this data from Cadence here, and then we just fix the capacitance that we need for the input capacitance, and actually the rest of the information we don't need, so we can comment. And then there is a piece of information that we also need of this transistor, and it is the corner frequency of the noise. For that one we have the noise template also. So we run our noise simulation. I will close this one. And then we get the following simulation result. We put in logarithmic scale. So the noise floor, it is around 1.1. It's 1.1, 1.01, 1.02 nanovolt. That means that the noise corner has to be around 1 nanovolt times square root of 2. That will be 1.41. So it has to be around here, around 60. Around 70. Around 71 megahertz. So 71 megahertz. We come back here, and then we are going to put FC is equal to how much was it? So 70 megahertz. It was in 70 megahertz. So 70 megahertz for this transistor. And let's comment the transistor that we had down. And then we just run this simulation and see what are the results that we get. And now first I just want to test my equation. I get some interesting things here. I'm testing my equation, and I will test my equation from 1 kilohertz to 10 gigahertz, and then I plot it, and then in blue we have the input referred spectral noise density, the total. In red we have the contribution only of the source resistance. In yellow we have the contribution of the resistors, and the transistor, the input transistor, we have the contribution here down. So basically what I did is that I split these contributions during the integration. So then we will see this plot with the different contributions, so I can track where are they coming from. Now I am actually interested only in 1 kilohertz to 1 megahertz, so I'm going to simulate only the part that I'm interested. But I can actually, before doing that, I can identify the different parts in this curve. You can identify, for instance, the 1 over f noise here. It's going to be here. I can identify the white noise, thermal white noise from the resistors and the transistors located here. And then the high frequency noise coming from the noise current source is the one that is going up at very high frequencies, above 1 gigahertz. Okay, so now that I identify the source of noise, then I will change this to 1 megahertz because this is my band of interest, and then I run the simulation again. And then I see that my noise, it is basically dominated by 1 over f noise. Okay, it's 1 over f noise of the transistor. And then something that I also did in this script is that I calculated the integrated noise over the band of the individual contributors, so it gave me a good idea of how much each part contributes. And then in this particular case, it is the transistor that is contributing with almost all the noise. Only very little it is contributed by the source and the feedback. And what it is worse, it is a lot of deterioration of noise, much more than I expected. In my original budget, I set as my target just to double the noise of the source. So we are pretty much off right now. And then yeah, basically I have to change the size of this transistor. And then now let's for a second assume that we don't have flicker noise, 1 over f noise. So I'm going to set this to 0. If I set this to 0 and I run this simulation again, okay, the 1 over f noise disappears. I'm going to check, and then I get something very interesting. I get that the source contributes with 75%, which is pretty much what very, very good. Yeah. The feedback contribute only with 20%, and then we have the rest contribution coming from the MOS transistor. So, okay. So when I see these numbers, yeah, then I can see that definitely is the 1 over f noise the problem. Okay, and then to reduce the 1 over f noise, then I will need to increase the size of that transistor. That is one thing. The other thing that I can see is that the transistor contributes very, very little noise here. Meaning that maybe I have too much transconductance here. So what happens, for instance, if I reduce this transconductance to 1 millisiemens, and then I run this one again. In 1 millisiemens, on the other hand, then I see that the MOS transistor contributes with too much noise here. So I can reduce this one. Let's put it 4. Then it starts coming to much reasonable values. Now it's 12. And if I put it, for instance, in 8, then it is contributing very little. So changing these values here, I can have a very good idea what it is going to happen at the end of the day when I simulate my circuit. So if I put, for instance, a value of 6 or 7, let's put 7 here. Then I'm going to start hitting very interesting values of around 10% and 20% for the feedback. And if I start giving also values here, let's have it, for instance, 1 megahertz noise corner. Then I can start seeing more or less which kind of transistor I will probably need. Probably if I reduce this one to 100 kilo, then I see we are getting some kind of results that it is close to what I will expect. So I will need to change this transistor. Definitely this transistor didn't work. This transistor bias with 1 milliamp didn't give me what I wanted. In particular, the main problem was the 1 over f noise. So I will have to change it, and for that I will have to iterate. And then one thing that I can do it is to change to a much larger transistor. So I will delete this one, and then I will try another option. Yeah. Um, since the problem was the 1 over f noise, yeah, and then from our experiments we know that around 7 millisiemens is transconductance, it is kind of okay. What we're going to do is we're going to increase the size of that transistor, yeah, and we're going to increase the size of that transistor. We're going to increase to 500 micrometer width. We keep the 0.18 micrometer, and then we're going to try this current. Actually, we can put these numbers and try to see the GM or ID curves for this one. So this is let's make it 20 times 10 times larger. So this will be 500 0.18. We save it, and let's first take a look to GM or ID of this transistor. So it is finished. Then let's put this in logarithmic, this also in logarithmic. We split it, and then let's see, we need around 6 or 7 millisiemens, and for this transistor, let's say for 400 micro for 400 microamps, I get almost 9 millisiemens, FT of 2.4 gigahertz, which might be perfectly enough in this application, and much better. I had also much better GM over ID. It went to 22. This with the 400. We can even reduce the power consumption a little bit, and we still probably with the 7, we need around 300 microamps to get around 7 millisiemens. That was the value that we were testing. So around 300. We are going to try with 350 microns. Let's put it in 350 microns. So we got here, and then we're going to put in 350 microns. This size of transistor we save, then probably that will be enough. We run our script to extract the small signal parameters, and then we get the information that we need. Let's move this one to our MATLAB script. We comment this millis. We don't need this. E minus 15, E minus 15, E minus 15, and we don't need the rest, so we can comment the rest, and then we need to extract the FC of this transistor, and then for that we use our template for noise simulation. We run the the simulation and then we extract. So the noise floor here will be around 380. That means that the noise corner will be 380 times 1.41, that will be 540. So 540 will be here in 39 and 40 in 40 megahertz around. So 40 megahertz we got with this information to our script, and then we run the simulation again, and then we get still we're a bit off with the we are a bit off with the 1/f noise. It is just too strong, and then I mean we can see it directly here. The contribution of the MOS, it really dominates in all the band of interest. Just for curiosity, if we reduce this to 4 megas, let's see what happens. Then we started getting a little bit better, but still 4 megahertz is still a lot, 1/f noise. So we need to change our transistor. Still it is too small and is injecting a lot of 1/f noise. So we go back here, and to now we have 350 micrometer, 0.18, and then now the transistor is 500 micrometer length, so the width, so it is quite a wide transistor. At some point we might have really serious issues of area, and we might not be able to increase the width like that. So there is some considerations that we have to make. So what we're going to do now is to increase the length of the transistor. So we are going to increase it to around the length to 0.5. So we increase the area of this transistor, and we are going to run a GM ID on this one. Okay, so we have log scale, and then we split it, vertical marker, and then we try to see where can I hit the around 7. So for around 7.5 I need like a 400, let's say 350 micro, a little bit more higher. Let's try to fix it in 400 microamp. It is okay. I have a FT of almost 900 megahertz, which is quite good, as it's much larger than the bandwidth of interest. And then the GMR ID, it is close to 20, which is not bad. I mean, the top it is 31, so I'm still close to the corner of the GMR ID. So my interest here is not going towards the right side, because then the GMR ID efficiency is very, very low. So still it is kind of okay. So let's take a look to the noise performance of these transistors. It is biased at 400 microamp. So let's close it, And then we're going to bias this one in 400 microamp. Let's save it, and then let's run noise simulation. Okay. So in this case, the noise floor it is around 1.1. It means that the 3 dB the corner will be located at 1.55. So it is 400 around 450 kilohertz. Okay, 440 kilohertz. Now we come back with this number, 440 kilohertz. And then I think I already have this transistor somewhere here. Yeah, it is already here. So we are going to comment this one. Actually, I can delete this. I don't need this anymore. These are all the transistors that I was testing before. So this transistor, that it is 500 micrometer width, 500 nanometer length, 400 microamps. This one has an FT of around 445 kilos. Then we're going to run this one. And then we have something interesting. The noise of the source becomes around 50%. That was my target. And then between the feedback and the transistor, it is around 45%. So then I think based on the theoretical part, it looks like it is okay. Now I can try this transistor now in a more realistic environment in the simulator and test if actually it gives this performance that my equation is predicting. So for that I will close this and then prepare a schematic. Okay, and the schematic looks like this. We have a self-bias transistor as that we have used before in front of an annuller. The model of the annuller in this case, it is just an ideal voltage controlled voltage source with a lot of gain. I put it 1000 here. Now we just have to make sure that we have negative feedback. So make sure that it is connected correctly, the output. In this case I had to connect it from down, so it is negative feedback. And then I will give the sizes and BGS and IDS and BDS from variables. And I have set here as global variables the drain current, the length, the number of fingers, the width, VGS that we extracted from our script. It is here. It is extracted from here, so we have those values also available easily. And then I put the values of the feedback that I calculated, so that they will not introduce so much noise, and at the same time not being too little, because of the current consumption that will be required to drive them. And then I set up a noise simulation and also an AC simulation, and then run this simulation. Then we have the input reference noises here, and then I have simulated over a large bandwidth, and then we can actually take a look how close these curves are with respect to the curve that I have with the MATLAB. That it is here. So let's just bring it, this one here, let's say at 1 meg. We have 4.83 nanos. Let's take a look here how much I have. It is 4.76 nanos, so not so far away. Now the easiest way to check if we are doing what we expect, we are right, it is actually to check the integrated noise, and for that we go to the ADXL results here, and then we just print noise summary, and then here we will select integrated noise, and then we can have it as a power or as a voltage. This is output noise, and then we integrate in the band of interest, in this case 1 kilohertz to 1 meg. We select all types of noise that we want to analyze, and I put the 10 top contributors here. We apply, and then we will get the noise contribution, and then R0. We can take a look here in our schematic. R0 is the source resistance. It is contributing with 64%. So no, it's not so far away to what we calculated in MATLAB. We have a resistor 1. It is around 15%, and the resistor 1 is located here. And we have resistor 2 is actually contributing with much lower. Remember that it is the parallel of these two, the one that give V12. So this is these two, and then this one that is smaller is going to dominate in this parallel combination. And then we have the noise of the transistor. We had around 14% coming from 1/f noise, and around 5% coming from drain noise current. So it is close to 20% coming from the transistor, which it is pretty much close to what we predicted using our equation. So think that the equation we use the Ks equal to thirds, a little bit conservative also, the 1/f noise, so we end up with a little bit over what we had during the simulation, but it is not much. It is around 10%. 10% is 1 dB, so it is not pretty far away to what we had from our MATLAB simulation. So we can really trust our hand calculation. We can trust that our equation is working. Normally give us really good matching with the simulation results, and it is actually a really powerful tool to do noise optimization, because we have control over each part of the design parameters, the size of the feedback, the transistor corner, and also the size of the transistor will be here for the capacitor. So we know exactly which parameter needs to be optimized depending on the bandwidth that we are working. Okay, with that we finish this exercise.